This concept of the Voronoi diagrams in the behavior analysis. What is a Voronoi diagram? In the classical Voronoi diagram, we need a generator set formed by endpoints in R2. With this point, we construct a polygon, a Voronoi polygon associated to PI, defined by this expression. Usually, the function D is the Euclidean distance in R2. And what is that? This set is the set where of all points where Pi is the nearest point of P to X. When we take the Euclidean distance, the edge of two adjacent Voronoi polygons are straight lined. The union of all Voronoi polygons is the Voronoi diagram. There are some differences with weighted Voronoi diagrams. Also, we need a generator set, but adding assigned weights W1 to Wn, and in a similar way we define the weighted Voronoi polygon, but now this is not the set of all nearest point to Pi. In this case, the function dw is not necessarily a distance in the mathematical sense, but in some sense, this is the set where Pi is the most important point. In some sense. The union of all Voronoi regions is the weighted Voronoi diagrams. There are many functions with that are weighted distance. We will consider a multiplicatively weighted Voronoi distance, where this expression is the Euclidean distance between X and Pi. And in this case, the edges are not necessarily straight lines, but the boundary of Voronoi regions are characterized by the following theorem. The edge of multiplicatively weighted Voronoi regions are circular arcs if and only if the weights of two adjacent regions are not equals. And are straight lines in the plane if and only if the weights of two adjacent regions are equal. In this case, the weights are equal, and in this case, or this, the weights are different. Well, what about the spatial behavior analysis? Behavior analysis constitutes a discipline that aims to understand the behavior of individuals, exploring both the behavior itself and the variables that influence it, including the spatio-temporal dynamics of the environment. Within this field, the study of organisms moving within the framework of behavioral phenomena and repertories addressed from perspectives such as organization, development, and change is termed as spatial dynamics behavior analysis, SDBA. In this DBA, one of the main challenges lies in visualizing quantitative relationships between spatio-temporal variables of the environment and spatio-temporal features of behavior, specifically a clear representation of the organization, development, and evolution of interaction between variables, such as the time of stay and a specific zone, and treatment variables, such as a type of reinforcement schedule defined by the spatial temporal constancy or variation in water delivery. And so, this approach is applied to study a specific behavioral phenomena, such as spatial differentiation in water-seeking situation and in water-deprived rats. The experiment were conducted by members of the comparative psychology laboratory at Universidad Veracruzana. The subjects were 12 Wista rats under water deprivation, and the experimental setup was a chamber 92 by 92 by 33 centimeters with water dispensers. The water dispensers were in the sides of the regions, and the data are 7,200 data points per session, 50 sessions, 20 minutes each. In this case, we have the intersection of two environmental features and two environmental dimensions in the experiments. Fixed time means water delivery occur every 30 seconds with an availability window of 3 seconds. Variable time means water delivery time varied with an average of 30 seconds with an availability window of 3 seconds. And fixed space, water was delivered consistently at the same dispenser in all sessions located at the coordinate 50,0. Variable space water was randomly delivered to one of the 4 dispensers. With these intersections, we have 4 kind of experiments: fixed time, fixed space, fixed time, variable space, variable time, fixed space, and so on. These are the means is the movement of a subject, and we use this data to construct the weighted Voronoi diagram. How? We divide the chamber in 10 by 10 regions, and we calculate the center of each one, and we use this center as the generator point, and the generator set is P. It's called the initial set, and in each point of the initial set was assigned its weight based on its cumulative time, and the generator set was defined as the set of points whose assigned weights were non-zero. We have a case where 0, and this point is not considered. The set of W contains all the weights corresponding to the generator set P, and then we construct the weighted Voronoi diagram with using Python. So We have some examples where we can we choose 4 subjects. In the first case, we can observe that the subject spent time in the water dispensers. The water dispenser is the red triangle, and also in the corners. Then in the last session, the predominance regions is this one, the green, and in the subject 7, the first session in both subjects is similar. In both cases, the subject spend the time in the corners and in the dispenser water. So the variability in time delivery influence of regions or behavioral relevance. So when in the case where the space is variable, we have the following examples. The subject for in 4 cases the first session is similar, but the last session has many differences. In this case, there are symmetric regions with the straight line arcs here and here. Then that means that the weights of the generator points are equals. So in the final session, we know that there are not straight lines. Then there are ranges more important, and the weights are different. Finally, we can show that this concept of the Voronoi diagram can be useful to study the movement of a subject. In conclusion, weighted Voronoi diagrams are useful for visualizing and understanding behavioral patterns, for identification of regions and behavior relevance, called RBRs, and also for evolution of RBRs over time and space, and it has potential for broader application in behavioral studies. That's all, and thank you for your attention, and sorry for my English.
Thank you, Doctor. Well, we have some time for questions for Dr. Carlos. Someone have a question?
I have a question. How did you follow the path of the rat under the square? Did you use a tracer
sensor,
or something
sí.
like? Yeah. Okay.
There is ¿puedo responder en español?
Okay. Yes.
Sí, se usa un sensor de movimiento que cada cierto tiempo ubica el centro de masa de la rata para asignarle una coordenada. Y bueno, pues se recogen todos esos 7,200 datos y para formar la trayectoria.
Okay. Y ya que tienen esos mapas de la ruta, ¿se cuantifica cuánto tiempo pasó en cada una de las regiones? Sí. Para pasar a los números.
Exactamente. Entonces las regiones donde no haya estado en ningún momento, no las consideramos.
Okay.
De cada uno de estos cuadritos, pues tomamos el centro y allí podemos calcular cuántas veces estuvo a lo largo de la sesión, y eso es lo que me da el peso. Entonces eso determina qué tan importante o no es una región para el sujeto de estudio. Y lo que se está haciendo en realidad pues es estudiar la evolución de los diagramas de Voronoi a lo largo de las sesiones, que va cambiando. pues en algún sentido el sujeto va aprendiendo, ¿no? Primero no sabe dónde buscar el agua y a lo largo del tiempo pues toma una decisión y se da cuenta que tiene que escoger un dispensador, ¿no?
Ok.
En este caso que el tiempo es fijo y, o sea, en determinado momento se asigna el agua y siempre sale del mismo dispensador, pues la ratita suele quedarse en ese lugar, ¿no? Cuando el tiempo es variable, entonces no sabe cada cuánto va a ocurrir, pues hay más movimiento, ¿no? Y los diagramas de Voronoi son más dinámicos, aparecen líneas rectas. Ya cuando nos aparecen los arcos de círculo, pues significa que una región dominó a otra, porque los arcos de círculo solo aparecen cuando los pesos son diferentes. Entonces una región más grande significa un peso más importante.
Y en este esquema podría funcionar también un modelo de Markov que, no sé, que calcule probabilidades de un estado dado otro, algo por el estilo.
Pues no lo hemos intentado, de hecho queremos seguir estudiando este tipo, bueno, en esta área, seguir trabajando en esto. Hemos pensado cosas con series de tiempo, tratar de encontrar patrones, no sé, como periodicidad o semiperiodicidad a lo largo de la trayectoria, cosas de esas, ¿no?
Ok.
O comparar si dos individuos se comportan de la misma manera usando sus trayectorias o cosas así, ¿no? Pero bueno, sería algo a considerar lo de las cadenas de marco.
Ok, gracias.
¿Alguna otra pregunta para el doctor Carlos? Sí.
Hola, Doc, gracias por su presentación. ¿Podría repetir con qué es con lo que miden el comportamiento? Dijo que tenía un sensor de masa.
Ah, aquí, mira. Este dibujito. Sí, la rata está en una arena con estas medidas y aquí arriba se pone un sensor de esta cajita, ¿no? Y lo que detecta es en qué posición, usando su temperatura, en qué lugar de la caja está la rata. Entonces determina una región, calcula el centro de masas, ¿sí? Pues se determina un área, ¿no? Estima el centro de masas y las coordenadas de ese centro de masa son el punto, ¿no? Que se le asigna de la posición de la rata.
¿Y cada cuánto, o cómo es la medición?
Si mal no
de los
recuerdo,
sensores?
cada 3 segundos.
Cada 3 segundos hace una
A ver,
medida.
aquí Alejandro me corrige. 5 frames por segundo.
Ah, ok. Y en este caso, ¿no han pensado implementar quizás alguna cámara de alta velocidad para tener un mayor espacio de frames del análisis que están haciendo? Digo, en este caso es aplicado a una ratita, ¿no?
Sí.
Pero digamos que miden el comportamiento quizás de un individuo, de algún objeto que tenga una mayor velocidad. Entonces, quizás aplicando una cámara de alta velocidad, eso permita que pues todavía la trayectoria sea más exacta en cuanto a las mediciones que se tienen.
Pues supongo que sí, pero era del material con que se dispone. De hecho, bueno, si no Alejandro me corregirá, pero creo que hay estudios similares de estudiar el movimiento con niños con autismo, ¿no? Entonces, claro que tu pregunta es natural, ¿no? O sea, se puede extrapolar esto a individuos que se desplacen más rápidamente y en ese caso, pues las necesidades técnicas serían mayores, ¿no?
Okay. Muchas gracias, Doc.
No.
¿Alguna otra pregunta? Bueno, yo tengo una con respecto a la red que utiliza, que decía que era de 10 por 10. Si se utiliza otro tamaño, las regiones que aparecen cambian. ¿O?
Sí cambiarían al inicio, ¿no? En el inicio se verían diferente, aunque a lo largo de las sesiones, dado que la ratita comienza a gastar más tiempo solo en algunas, el diagrama final sería similar, más o menos. O sea, podría tener algunas pequeñas variaciones, pero sería similar. Al inicio podrían ser muy distintos, dado que el mallado es diferente, pero conforme vaya avanzando el experimento, sí, creo que se estabilizaría. Probablemente creo que sí podría haber mucha diferencia en este caso, ¿no? En el que las dos cosas son variables, tanto el tiempo como en el espacio. Entonces, a lo mejor allí algo más fino podría funcionar. Bueno, depende de lo que se quiera estudiar, ¿no? Dependiendo si queremos dependiendo de lo que se quiere estudiar, se podría tomar más fino o más amplio, ¿no? O si digamos que ahí sí, como es un trabajo multidisciplinario, ahí sí interviene el experto, ¿no?
Bueno, si no hay más preguntas, le entrego su certificado por su presentación y muchas gracias. Okay, our next presentation is pattern recognition in road safety, uncovering the latent causes of accidents on Mexico's federal highways, presented by Diana Cepeda.
Thank you. Good morning. I collaborate with Doctors Angelica Guzman, Doctora Rosa Maria Valdovinos, and David Delgado, and I am Diana. And I have some questions for you. Have you ever considered the importance of land transportation, specifically highways? How many times have you traveled on the highways in recent months? Traveling with highways often make us feel free, allowing us to explore environment around us. And let's recall some personal experiences on the highways. Perhaps it was when we went on that special dates with our loved ones, or that dream vacations with their family, or maybe it was attending a business meeting on the other side of the city, or participating in a recognition partner event in Xalapa, Veracruz. Every trip gives us the opportunity to discover new places and create unforgettable memories. On the other hand, most of the products we have and we consume every day have come to us thanks to road transport. This system logistic is essential for facilitating trade, connecting regions, and ensuring that goods reach their final destination. But according to statistics of Secretary of Transport in 2021, more than 2.2 billion passengers and more than 513 million of tons of goods were transported by highways. This makes highways the main means of transport for both passengers and goods. However, all this movement carries its own risk. I'm going to show you a video to demonstrate that. Have you ever noticed traffic speeding up and slowing down during your trip? What is the first thing that comes to your mind? Maybe something happened or it was an accident. Well, as we move forward, we see these images like this or similar. Or maybe when we turn on our TV to watch the news and something accident happened. This is a very bad situation, and in 2017, in Mexico, Cuernavaca highways occurred an incident like this. All this video that I show you is recordings of accidents. In 2020, 13,630 people died from injurious traffic accidents, corresponding to a mortality of 11 per 100,000 of inhabitants. As we can see, statistics is a decrease compared to 2015, a decrease of 18.9%. Data from National Security Commission show that the main cause of death of road accidents occurs on highways. According to the National Association of Private Transportation, each year road accidents cost the country 150 billion pesos, which equivalent 1.7% of national GDP. But we have the question, what are the causes of these accidents? For this, we use two methods. First one, lack the translate allocation and K-means. LDA is a topic modeling technique in machine learning to discover hidden topics in a collecting of documents. It's a mix of features. For this, we use two variables, perplexity and coherence. Perplexity determines how efficiently a model can handle previously unobserved data. On the other hand, coherence evaluates the clarity and consistency of the issues from a human point of view. K-means it's a unsupervised learning model which collect objects and to make groups. That groups are known as clusters based on their characteristics. Its objective of this model is minimize inertia. Inertia is a measure that determines how current the clusters are. Our data set that we working on that were extracted from Mexican government official website. We include 16,008 samples of traffic accidents between 2015 and 2019. With these characteristics, we use, with that data set, we find hours, kilometers, highways, victims, all that characteristics that we need to do the study. But the final data consists of 50,917 samples and 15 attributes. It's because when we checking the data, we identify that the data that we have original had characteristics that doesn't necessary for the study. For example, characteristics of the vehicles, something that is not important because we are studying causes of that accidents. The processing of data also were adapted with requirements of LDA. For this, we need to transform text into a textual format because we need to generate groups, or in this case, topics. For K-means, we kept numerical on what coding was used and adjust them. So we work on categorical variables, which represent the presence or absence of the numerical value. Overcoding latent patterns. Well, for this graphic, we observe the relationship between perplexity and coherence. We determined 10 topics because the optimal configuration for the given model prioritized the perplexity reaching is the lowest value with 10 topics. For k-means, we use Jambu's elbow to determine the number of groups of clusters. In this process, a decrease in inertia is observed as the number of the clusters increase. The appropriate choice is identified at the point where decrease inertia samples. For topics, we choose 10, and for groups, in this case, k-means, 5. Results. We have first a word cloud from topics that, if you can see, there are a lot of words. In these words, we determine of results. First for LDA, in Nayarit, Puebla, Tabasco, and Tamaulipas, most of the accidents over in the mornings or 3-lane highways influenced by adverse weather conditions. On the other hand, in Mexico City, incidents mainly due to lane in knowledge, while in Aguascalientes, Nuevo León, Jalisco, and Tabasco, accidents were frequently on Sunday on mornings during the fall to yield. In Yucatan, Durango, Sonora, accidents were concentrated in specific month days. In addition, the state of Mexico. During the Day of the Dead festivities, and the states like Guanajuato, Chiapas, and Tlaxcala experiment an increase of accidents. In December, neck accidents were related with weather conditions, and drivers were reckless. For the other groups of words that I have is k-means. We identify similar groups of data. In this case, clusters analyzed using k-means provide us a clear view of specific patterns of road accidents in different regions and periods of the year. Guanajuato, Jalisco, Chiapas, San Luis Potosí, State of Mexico, incidents were recorded, highlight those during at night and early hours of morning, mainly Sundays and during the month of December. Why December? Because it's the particular festivities like a New Year and Christmas. These events are linking also with the weekends, so it's more common to appreciate these road accidents in these periods of time. K-means were compared with LDA through metric, silhouette metric, and K-means highlights the importance of careful selection of clusterings, methods, and highlights the robotism of K-means and the concept of road analysis. For our conclusions, we have traffic incidents in Mexico are one of the leading causes of death and injuries, and the methods provide an understanding of driver behavior, road conditionals, and temporal factors. As I mentioned, some words, but I would like to remember a moment, because thinking about your trips, have you ever related some trips with some of words like this? Thinking about your answer. And actually, for some measure activities that the governments are doing, it's like a campaign, Carreteras Seguras, and they promote the security for all passengers. Maybe with don't drink or don't use cell phone and the other signals that can protect us. I don't know if you remember the first question. It's like how many have you traveled in the highways for recent months? But it's very important to raise awareness, because accidents are more presented than we know, and I showed you in the first slide. So I would like thinking, what will happen if some situation like this you can see, or maybe you are near? Faster or slower, they're only an accident. In life, on the road, safety comes first. At home, they are waiting for us, and then prevention can save our lives. Thank you so much.
Thank you, Diana. Well, we have time for questions for Diana. Anyone?
Well, first of all, thank you for your presentation. It was very interesting. So I have a couple questions. First of all, I want to know if you have tried, for example, to estimate or compare with density, because I also believe that perhaps, well, I want to know if the rate of the accidents depend on the density, because you also say that I believe Sundays and also December it was the month with more activity in this case. So have you ever tried to ponderate or to find a relation between the words and also the density?
Actually, no, but maybe we'll work on that. Only we find the causes, the main causes, or the accidents, but obviously we can continue with that area. Thank you.
Well, thank you.
Any other question?
In your approach, you use two methods. One is supervised, and the other is not supervised. And LDA is a supervised approach. Is it? I am right?
No, both are unsupervised methods because both needs don't need preparing data for the model. Only
Okay.
you can use. In my case, I only need to convert the data for textual and for
Okay.
categorical data, and then I use the model. But it's not necessary. It's unsupervised data.
Okay.
Methods.
Okay, thank you.
Any other question? Well, thank you, Diana. Thank you. The speaker for the next presentation. Okay, our next presentation is a regression tree as acquisition function for low-dimensional optimization, presented by Eric de la Paz. And I think
Good morning, my name is Eric de Paz. I'm a student in a research center part of the Secretary of Agriculture, and my exposition is about a novel optimization method. Well, optimization is the process of finding the minimal or maximal of a given function. The most popular methods are based on calculus theory. There exists a lot of methods for optimization. Another popular approach is to iteratively resampling over the domain to eventually converge to the optimum. And the first part of my exposition is about a not very popular family, the branch and bound family of methods. These methods are based on the following hypothesis. For a small difference in the domain, it corresponds a small difference in the codomain. This simple idea can be formalized in the following expression. The vertical difference divided by the horizontal difference is bounded by a constant. If we know this constant, it's easy to bound a function. by means of a central observation of the middle of the search space. This is a very basic idea. It's just create a bound for enclosing the function. For example, the direct algorithm divides one optimization problem into two optimization problems. Each resulting optimization problem has a smaller search space, so it's possible to define more specific bounds. This idea is applied recursively, and then it's possible to find the most promising point. This idea is very slow and limited or well restricted for lower dimensions. A probabilistic alternative is called optimistic Bayesian optimization. This idea is based on an stochastic model, and a stochastic model which defines a credible region. This credible region is defined to contain the most likely connecting paths between two observed function evaluations. So in the most of cases, the octal function is contained inside this region. This region is also called acquisition function because it's useful to identify the most promising point to evaluate. The maximal point inside the region is a promising point to evaluate. This new evaluation allows to define more specific regions, and as before, we repeat this process. Well, in this context, our idea is applying a machine learning method instead of using a constant for defining this boundary, or modeling with a very sophisticated stochastic process. To discover the most promising points in the function, we modeled the function with a card model. Card means classification and regression tree. A regression tree consists of dividing the search space into subsets and then assigning an approximated answer for each subset. These kind of models may be updated to improve the approximation, and this is the process to update a card model. We randomly select a subset. The probability of selection is proportional to the size of the subset. In this case, we are going to select the greatest one, the subset in blue, and then the subset is divided in an optimal partition. This partition is optimal because it reduces or it minimizes the difference between random evaluation of the function and the approximated answer. It's a very intuitive idea. Just we're trying to learn the function, and then with this model, it's possible to decide, hey, this is the highest part, this is the most promising point to be the optimal. However, it's very, very slow. We're trying to learn a function in all the search space. It's an innocent idea. Well, to model only the most promising subsets, we propose the following modification. As before, we randomly select a subset, and then we verify if it's a promising subset. A subset is not promising if a random evaluation of the function is under the maximal observed at the moment. So that's not a good subset. And we back to the first step to select a new subset. A subset is accepted as promising if a random evaluation inside the subset is greater than the maximal observed at the moment. If the subset is accepted, then we divide the subset, and it's possible to update the model of the function. Well, this cycle is useful to concentrate the sampling in the most promising regions of the search space. Now, the probability of accepting a subset and the posterior probability are easy to estimate by means of statistics of the card model. This posterior probability is very, very interesting because consider this. Under the assumption of having accepted one observation of the function, we can identify which is the most likely subset to contain such accepted evaluation, such accepted observation. So this cycle for searching a promising subset, it's not necessary. We only compute this posterior probability, and that's all. So we don't need computing a lot of observation. Just based on the previously data, we compute this posterior probability, and this is the method that we are using to select the most promising subset. This is the most important point of the paper and is the only difference between a regular card model. Well, results. The results depend on the geometry of partition. In the paper, we reported a triangular partition like this. And no parametric tests show that our approach is better than other popular algorithms, but only for the initial dimensions. Well, however, our approach is consistently better than the most popular branch and both algorithm. That's something, and even more. This sort of regression tree based on a triangular partition is restricted to lower dimensions. In dimension 2, we can see triangles, but in higher dimension they are called simplexes. And in higher dimension it's quite complex it's getting harder working with this geometry. So for evaluating our approach in higher dimensions, we implement a rectangular partition. This geometry seems not very proper to fit a function. However, in higher dimensions, well, not so high. In dimension 30, 50, and 100, non-parametrical tests show that our approach is very, very competitive. I'm not an expert in optimization. I'm just like a little child playing with models. And these results, well, for me, these results, this comparison versus differential evolution is amazing for me. It's impressive. Well, I'm the author. This conference paper is the main reference for software library. If the R Foundation accepts this library, we hope that, you will have the chance to reproduce these experiments. It's important to reproduce this and discover, hey, that's true. He's not lying. Well, do you have questions?
Thank you. We have time for questions. Anyone? Okay, I have a question about the last slide you showed. In here, you generate the data or how the results, yes.
It's a very important point that I forgot to explain. These tests are performed with a standard collection of benchmark functions. Well, we decided to use this version of the Computational Revolutionary Congress. I don't remember the specific name. In this year, this old version of the benchmark collection, because there are 12 functions, and we need to reproduce these experiments a lot of times. So we need a small benchmark, a set of benchmark function. However, it's commonly reported in literature. The family of functions includes ACLI and there are many functions. And one of the most easy functions to optimize is the spheric function. This is just a circle that you have to find the minimum of that. It's the most easy function to optimize. But there are even harder functions. That's a pretty question. Thank you.
Anyone has another question for David? For Eric, sorry. No? Okay, thank you, Eric. Isn't here the next speaker? No.
Hello, yes, I'm here.
Okay. Well, our next presentation is missing data and their effect on algorithm selection for the bean packing problem, presented by, I guess, Ana Karen Garate Escamilla.
That's correct, it's me.
Yes? Okay.
Just give me a second, I think that I'm hearing a little
Yes, thank you.
not well, but maybe my system. Let me check. Yes, I think a little better. Give me a second. I will share my screen. Okay. Oh, give me a second. Let me share my second. Okay, okay. Are you observing my screen? Okay, thank you. Okay, can I start?
Okay.
Can I start?
Yes, please.
Okay. Can anyone, well, the host can mute the other participants, please? It's a little noise for. Okay. Well, hey everyone, my name is Ana Karen Garate Escamilla, and I'm honored to be here with you to discuss an important topic in the field of optimization, that is the missing data and their effect on algorithm selection for the bean packing problem. This work has been done by Jose Carlos Ortiz Baylis, Hugo Terashima Marin, and myself. Second. Yes, I want to have okay, well, the laser, well, I can have it here in the presentation. Our motivation comes from the fact that there is already a lot of work on algorithm selectors, but we always assume that we have all the necessary data to establish a relationship between the problem the problem characteristics and the best algorithm that will be our solver. So for this work, we are going to use neural networks, the multi-layer perceptron, to implement algorithm selector from the one-dimensional beam packing problem. The, the heuristics are passed to a classification table. And for the neural network, we didn't do any hyperparameterization. An additional one we didn't do. And as we discuss later, missing solver information can change the recommendation of algorithm selectors. So what our question is, how much does it affect us? This is what we want to explore in this paper. And we explore the situations involving missing values and their treatment to observe the impact on the algorithm selector generated. The table that we have here, the above, shows us an example of the complete data for each instance in the training set. The training set, these instances were using neural networks. We show three characteristics, and the best heuristic is the one with the highest value. For example, here is A3 with 0.944. And in a case of a tie, a random decision was used. So having this complete table, we can observe the results. However, if the results of the algorithm are missing, the algorithm selector might learn different patterns. This is the example if we use we add new values. Two cases have changed from the complete table to this one in below. In this example, the algorithm A2 will no longer be considered by neural networks as the best selection. In this case, will be A1. And before we observed that was A2 with the point of 1. Sorry, with the result of 1. Continue the next part. What is the beam packing problem? The beam packing problem is a well-known combinatorial optimization problem where the objective is to pack a set of items with different sizes into a finite number of bins in the most efficient way. It has a lot of applications. We can see it in cloud computing, in logistics, in supply chain management, in different fields. An everyday example that we can observe is packing our clothes for a trip. We have to fit all our clothes, and we try to minimize the numbers of suitcases. And that's the point of the big beam packing problem. The beam packing problem, honestly, is a test scenario. It could be any other heuristics problem. So we can have this problematic in another combinatorial scenario. We have different ways to solve this. The first fit packs the item in the first bin with enough capacity for packing the item. The worst fit packs the item in the bin that maximizes the waste. Almost worst fit if the second most waste produced, and the best fit packs the item in the bin that minimizes the waste. We can observe in this, we can ask, how does each heuristic pack the next item? And I'm going to the next slide, and we observe the way that it packs. The first fit here, in the first one, the worst fit in the one that has the most waste, the almost worst fit in the second one, and the best fit they do in the one with the less waste. For the instances that we use for this problem, we produce two sets of beam packing problem instances, a training and a test set. And this one was using an evolutionary approach. We generate them with the evolutionary algorithm. The two sets contain different instances that allow the heuristics to exhibit opposite behavior to these sets. And an important part that I want to add is this one. If we observe the training and the test sets contain 100 and 400 instances, each with 20 items, a bin capacity of 64 units, and a maximum length of 32. Honestly, this scenario is on for test. The idea before moving to something that is bigger. For this part, we can consider for the problem of optimization that this is small, and the idea was to test that first, and next we can try this to a bigger scenario. For the problem characterization, we also consider the length that indicates the average length of the limits within the instances. The value is normalized by dividing the actual average by 32. The small practically represents anything smaller than 0.5, and the large, the proportion that is larger or equal to 0.5. This is an example of the way that we can see the characterization, that we can see the length, the small, and the large. For our missing values, we are going to start from the training set, and we are going to introduce missing values. The training set, there is going to be a set that doesn't have any new information. Then we are going to produce from this training set 6 versions of the training set based on the proportion of the missing values. From NA00 that has 0% of new values to NA of 25% that has the 25% of the missing values. In this case, we have the percentage of 0, 5, 10, 15, 20, and 25 missing values. And these missing values will only affect the heuristics. They are not going to affect the features. So in the case that in one scenario that we are going to use the data imputation, the NA will be replaced by the median. For the experimental setup, here can be a little more clear the thing that I said before. The NA00, the training set, this is the complete training set, 0% of missing values, and we have 100% instances. Here, the NA generator will be divided in five another sets that each one has 100% of instances, and the red box determines the percentage of missing values, 5% to 25%. Next, here we can see the complete cases and the data imputation. The complete cases is the module that keeps only the complete cases. So for this part, in this scenario, with the 5%, the complete cases were the 80%. So we have a different number of instances. For the data imputation, we have the 100% because we impute the data with the median. So here we didn't ignore the null values. The null values were imputed by the median. And the instance level is the module that have the best heuristic for each one of the instances. And well, at the end, the test set is the test that we use for the test part of our model. We have 3 experiment results. The first one is no treatment for DNAs. The second one is working only with complete cases. And the third one was using the data imputation. I will go back to the first experiment. We use them with 3 neural networks, and we test this. Honestly, all of them, if we observe this part with the null ones, they perform poorly with the nulls. The remarkable thing that we are going to observe in the 3 experiments is that it doesn't matter the percentage of these null values, the results were almost the same. And for example, in this part, when we don't have any NAs in the data, the neural networks are learning to discriminate and choose a suitable heuristic for each case. And if you observe, they trying to mimic the best heuristic. This one here will be in our example, the best fit. That's what, when we don't have any news, they try to mimic this. And the strange part is that in all the cases, the other ones, the first fit was the one that they try to mimic. Here, in all the news, they try to mimic this part, the first fit. Honestly, well, in the part of machine learning that they select things in a random way, that's the reason that we have this part different, but it's only because of that. But they are trying to mimic the best part, the best fit, the best heuristic, and here, as I mentioned, the first heuristic they are trying to mimic. And it doesn't matter the data imputation also. No improvement was observed with the respect of the first two experiments. And that part is important also. And for our conclusions, we suggest that missing values affect the training process and the resulting selector regardless of the treatment used. What we think, or an explanation of this, is that the missing values and the imputation also may alter the label of the best heuristics for an instance. In a bigger picture, this can deliver in a contradictory cases that can make that the training could be difficult, and we need to have more experiment to confirm our initial observations. And that brings us to our future work, because we think that we also need to work with missing completely at random scenarios for the missing data. More than that, we need to have a more complex scenarios, such as missing at random, missing not at random. We need to work with these three parts and add them also with more machine learning models. For example, logistic regression, support vector machine, decision tree, random forest, a probabilistic model like Bayesian. So we need to combine these two ideas to make the work more robust. And for my part, this is all. And thank you all for coming here today and listening to my presentation. Is there any question?
Thank you, Ana Karen. Well, we have some time for question for Ana Karen. Anyone? Anyone? Okay, I have a question about the
Okay.
process that you are comparing in your slide. Yes, no, in the following slide. Yeah.
This one?
Why the first four elements are pink, or why they are not applicable for the model with the treatment for NAS?
We can take them as the, well, kind of the real scenarios, the scenarios that without this machine learning process that we are doing, the one that they can have in the heuristic way. If they use the models of the heuristic, the first, the worst, and the almost worst, and the best fit, if they use them, these are the results. That's why they don't change. In the experiments, this is our base. We can take them as the base that we are doing, and the best scenario was using the best fit. That's the best one. So the best part will be that, okay, that all my missing values can act like the best fit. But in reality, even if wasn't if the first fit wasn't the worst, in my opinion, looking to the box plots here, if not as good or if not that good as the best fit. So that's why they don't change. It's like our kind of a real scenario with the instances. And we try to training, testing the models, trying to mimic the results. The best one, of course, but in the reality, when we test them, I think that I think that they didn't do that well, honestly, when we have missing values. Also, I think that trying another approach of machine learning of different approaches can help us to understand that, or at least to can generalize and say, okay, I try 5, 6 machine learning models, because also the neural network was really small, the one that we use. You don't imagine that was an extremely big neural network. The architecture was really, really small with not a lot of neurons, because the problem was small.
Okay, thank you. I think my problem is this type of graphics is difficult for me to understand.
The box
But
plots.
yes, thank you.
Okay, it's not a problem. I can explain that. Oh, thank you, thank you. The
Any
box
other
plots,
question?
sorry?
Any other question for Ana Karen? Well, thank you for your presentation. It was very interesting. And we
Thank you.
thank you in general for your participation in the Mexican Conference on Pattern Recognition. We send you your constants of participation. And here we end with session 6 of this conference. And next is coffee break, and we see you in session 7 for the afternoon. Thank you.
Thank you. Thank you for all your support, also for connecting in Zoom.
Thank
See
you.
you tomorrow. Bye bye.